All right, Fender Productions presents our current chapter in Understanding Water. Okay, so let's go back to the time of ancient Greeks. Okay, ancient Greeks would have said that water is made up of particles, and particles are just represented by simple things like a circle, let's say. Okay, if you think back to earlier in the spring, you guys made electrolysis apparatuses with Gatorade bottles. So you had like a bottom of a Gatorade bottle, and then you had like the cap, and then you had like and then there's like a 9-volt battery right here, and then you had a tube over one 9-volt battery and a tube over the other 9-volt battery, and then there was a liquid in here, and you were collecting bubbles. So there were gases that were collecting. Figuring out the lighting here. There were gases that were collecting in these two tubes. What you found is that in water, there is a ratio. This should be maybe about twice this volume. So there's a ratio of 2 parts or volumes of hydrogen to 1 part or volume of oxygen. Okay, so you can pause right here and try and remember, what did this ratio of 2 to 1 allow us to infer about the structure of a water molecule? Okay, so what that allows us to infer is that a water molecule must have 2 hydrogen atoms, H, and O. Okay, so now we can say that the formula is H2O. But this is as far as our evidence has gotten us with regards to water so far. What we have now, though, now that you've done your whatever I decided to call it, where you're trying to see how much water you can get to either stay on the top of a penny, or how much water you're trying to get to remain in a glass, so that you can add pennies or nails or something to the water and get the water to sort of dome over and create this really cool dome that appears to be unbroken for a little while. What we need to start thinking about now is, how would we draw water? And how would we draw water so that it's consistent with what we saw? Okay, so if let's say we're working with a penny, or let's work with a glass. Okay, this is a glass. Let's say a glass of water. And as you add enough water, you actually get this really cool dome that appears, something like that. Okay, this right here is just the level of the tops of the edges of the glass, but the water goes above that. And so we need to sort of think about what's happening. Okay, if there's water up here and water right here, the water in those places is sort of actively resisting gravity. Gravity suggests that if the glass is already full, the substance should just sort of spill over, right? But that's not what we see. So that must mean that these water particles must be sticking to each other. Water particles, let me not go outside the frame. Water particles must be sticking to each other. Okay, so now what do we know about things that stick to each other so far? Okay, there's a term that we've used a little bit, and it's this term polarity. And it refers to the idea that something can have positive and negative charges. So positive or negative charges or partial charges. Okay, so that means that something can also be called a dipole. And if something is a dipole, it means that it has two poles, right? Like a north pole and a south pole, a positive pole and a negative pole. So if we know that dipoles and things that are polar in general stick to other things that have positive or negative ends, then if we know that water particles must be sticking to each other, then we know that a water particle or water molecule must be polar. It has to, because otherwise, thinking about a hypothetical otherwise situation, otherwise water would not stick to itself, at least so far as we know. So we can infer that water particles must be polar. Okay, so now let's think about the structure of water that we're working with. Okay, we have, I'm going to make sure I remember what the boundaries of this camera frame are. So again, we're starting with H, and O. Okay, so we need this molecule to be polar in some way. So it needs to have a positive and a negative end. We don't really know anything about the properties of hydrogen and oxygen at an atomic level, but we can start playing around with shapes. So let's say we take H, O, and H, and we just draw it that way. And we're thinking about the molecule being symmetrical in this way. Okay, if a water molecule is linear like this, like in a line, then it doesn't seem like there would be a positive and negative end, because this end is the same as that end. So it doesn't really make sense to say like, oh, this is the positive end and that's the negative end, because the whole thing, like both sides are the same. So we can't say that. Okay, so in that case, water is probably not linear, because if it's linear, it's in this way with hydrogen on both sides, it's probably not going to be polar. So water is probably not linear. We could have H, and O like that. We don't know a whole lot about bonding yet, but this is a little bit, this might be a little bit funny, because if we draw this way, then this hydrogen has one bond to this hydrogen, but this hydrogen has two bonds. And we don't really have an explanation as of right now for why a hydrogen atom would behave differently in two different situations. So right now, one assumption we may want to make is that all hydrogen atoms will behave the same way when bonding. So an assumption that we should probably make is that all hydrogens will behave the same. It must be late. Wow. Behave the same when bonding. Okay. So if we're saying that all hydrogens will behave the same when bonding, if that's our assumption, it seems logical, because hydrogen is hydrogen. One hydrogen atom should have the same properties as another hydrogen atom. Otherwise, maybe we should call the two atoms different elements. So anyway, it wouldn't make sense for these two hydrogen atoms to bond in different numbers. So this is probably logically not a very logical way of organizing these atoms. Okay. So if we want hydrogens to behave the same when bonding, then it does kind of make sense to put an oxygen in the middle. But again, we can't have a linear molecule, and so maybe we need to have something that's not linear. So maybe if the hydrogens can somehow be at an angle, then at least, on one side of the molecule, I'm going to get out my other marker color here. At least on this other side of the molecule, like this side, let's say, this side of the molecule will have the hydrogens, and so it will have some sort of property, whereas this other side of the water molecule, like that, has no hydrogens. And so this side would behave differently than this side, supposedly. So far, this is a logically reasonable proposal for what the shape of a water molecule could be, given the evidence we've seen so far, and by making this assumption right here about how all hydrogens maybe should behave. Okay, so last thing before we get to kind of the next step in our journey here, we have to answer some questions. 2 questions to be precise. 1, why would water not be linear? Why would water not be linear? Like, what is a possible explanation for that? Or how could water not be linear? Maybe that's a better way to phrase it. How could? Sometimes we have to change our questions. How could water not be linear? Okay, and 2, how, what's going on with the bonding between oxygen and hydrogen to make water a polar molecule? So maybe how does bonding lead to polarity? I'm going to leave it right there. Okay, so this is going to lead us into our next series of videos. And I just want to add in, we're going to get into a topic here called electronegativity. So keep an eye out for this word, electronegativity. Okay, this is going to turn out to be a really core concept. And I didn't spell it right. All right, so these are our questions for now. But again, what we just did, we just went through a logical sort of thought experiment to reason through how we can be relatively sure that water should be a non-linear polar molecule, because that's the only way that we can logically explain why water molecules would stick to themselves when they are bulging out of a glass or bulging on the top of a penny. All right.